Alright, welcome. No, wrong start. Yeah, it's another Draft Physics, Draft Science on YouTube video presentation. Been some complaints about volume of the videos, and sorry, really. I mean, I'm using Linux. It just doesn't really provide any tools to increase it by much. And it's not that far off of the low standard. I mean, the minus 12 is supposed to be the standard, and I'm somewhere around 15 or something. So maybe I can get up to a minus 12, but we'll see. Anyway, sorry. I'm not going to reprocess every video to increase the volume. I don't think I'm going to do that. We'll see. I certainly don't feel like doing it. Nothing inside of me is saying, oh yeah, I just can't wait to reprocess the videos. Anyway, for the 4 people that need more volume because they're in a crowded room or something, I mean, it's really not that low. Anyway, on to the show. Yeah, so light, these patterns. This particular one, the interferometer style pattern, and its creation and what really can be gleaned out of it and understood about it. But it really just has to do with the whole thing of what is light and what is it doing, and who knows, who has the right answers, and whether conventional physics has any correct clues at all. And I would say they don't. So this video will contain some speculation, some draft statements, but ones I'm fairly confident about, frankly, in terms of understanding what frequency is and all of this stuff, and whether it means anything to the individual photons. Frankly, they're just soldiers, and they really don't have any concept of, I'm a wave of something. They're just doing their individual thing, and they really don't have written on them somewhere, I'm a piece of light that has a certain frequency. That's not how they're living. Anyway. So this was just a very good, somebody did, a very nice experiment, and they said everything's very precise. You can see how clean the lines are, but you can see obvious features. The black parts are always about the same size, except right in the middle. The amount of space occupied by, what the hell was that? Anyway, the black edges, the lines are, the part of destructive interference seems disproportional. I mean, it has more of a consistency than the light lit parts, and so it's unlike the slit experiments in the sense that there is this huge difference between the bar size as you go across, having to do with, obviously, something to do probably with some sort of round geometry. But anyway, I will cease to speculate on that. So anyway, just thought I'd show some of that. And then I think we'll do a Professor Lewin video. I guess I'll premise it with a few arguments and such. So I'm arguing, see, they have an argument that a photon is a thing, okay, that it's whatever it is, it's this, sorry, let's just draw it their way. It's some sort of wave thing in 2 different fields, sort of, you could say, like a DNA molecule, except you're supposed to see them as in different planes, this magnetic and electrical thing. They really don't talk about its size, its length, as it being something real. They think this is now momentum frequency, so the closer together these nodes are, you could argue, the more momentum it has. That its frequency is its momentum kind of argument. It's moving the speed of light. See, I would argue that what a photon is little bits of stuff, and they're all moving the speed of light, the little bits, and they happen to be at a frequency. That is, bullets at a frequency, and the bullets are fired less than perfectly in a straight line. So if they were to hit a target, they're a little bit off. They don't all hit the exact same point in space. And that this polarization dimension is actually a couple of thousand atoms in width. So one piece of the photon hits an atom here, one piece hits an atom here, or an electron to be specific, electron that's part of an atom. Another one hits over here, and somehow that is conveyed through a material object that may be transparent to the other side, and there's an equal change in the environment on the other side. So these bullets hitting this surface change the surface, it's transmitted, or it can be reflected. And that's the interesting part, is the reflections, is what's getting reflected. So in examples like the single slit experiment, I would argue that what's being reflected is sometimes a particle, the light's coming here. This is we'll call this the average. Some of the bits are up, some of the bits are below, some are up. So some of them get killed because they actually do hit a surface. And so the frequency of the photon is lost. And then some make it straight through. And so some have some part of themselves destroyed and some don't. And then there's the other problem of they're going through this surface that has electrons in it. And so the path of the photons is also being changed. But it's the path of little bits. So one bit ends up going over here after it hits a surface, let's say, and one bit goes this way. So they're being broken in two ways. First, they can be broken by having some portion of these bits absorbed by a structure, or like in a polarizing film. The difference would be that the polarizing film has a surface that's something like this, and so this represents a 2x change in its phase. That is, it slows it down twice as much as this slows it down. So this slows it down twice as much. This is just once. This is 2x slow down. Slow down meaning it's caused to do something less than a straight line. So one surface creates twice as much of this stuff as going through the other one. And so it's out of phase. So the two aren't in phase. The photon that goes through this thinner part has a different phase than the one going through the slower part. So this one goes further than this one. So they end up out of phase with each other by one wavelength. So they started right next to each other, and they would end up out of phase going through the polarizing film. So the film doesn't destroy anything. It doesn't break anything, essentially. It doesn't consume any of the photons. It just creates phase problems where the photon goes in with a frequency, and certain elements of the photon are changed in phase, and so you lose the frequency of that particular photon. So some get changed forward, some get changed backwards. They're just getting mixed up. So the little soldiers were coming in at perfect waves, and they come out not so perfect. Okay, they come out with some of them here, some of them here, some of them here, some of them here. So they come out in phase change, where half the soldiers have been put in a different location. Well, it's really not even accurate. They really come out still coming out like this. It's just that the element from this photon ends up here, and the element from this photon ends up here. And, they end up in the wrong order. So the platoons are mixed up. But anyway, I don't know if I would need to go into that particularly. So the subject Professor Lewin's going to deal with, apparently, is a prism. And I'm sure it's just going to be the math of the prism, but he's going to probably illustrate to some extent. And this idea that light comes in, it goes into the prism, it refracts, and their argument is that it refracts in specific ways that make the color. So like a red photon here is somehow just red changed. There's a specific change that only happens to red photons, and a specific change that only happens to blue photons. So if blue ones come in, they only do a specific thing. And the truth is, it just doesn't matter. The little bits, so if I have red photon and I have blue photons here, the little bits are exactly the same in the photons. You can make a red photon out of a blue one, you can make a blue one out of a red one. The little bits are just little bits going the speed of light. So when the little bits are interacting, the material can't tell, oh, this is a red photon. That is, the little bit is a red one, or the little bit is a blue one. It's always a little bit moving the speed of light as far as any material cares. And all you're really doing is seeing what photons are put back together. And that just has to do, again, with this path length difference. So whenever the photons have a path length that changes, they're coming out of a surface and one thing comes out straight, one thing comes out from at an angle. Well, this extra path length can be one phase. So it's like a phase change. Going an extra distance is the same thing as going through a thicker amount of surface. So just like the polarizing film, you're creating a phase change by having coming from a different angle. It's the same thing. It basically can undo what the polarizing film did. So and vice versa. So you're just talking about changing the phase. That is, cycling this little bit one cycle, moving him from this position to this position. And so you had two photons, obviously, and with broken pieces, you could understand that if I could move this one and there was nothing in this position, then if I move this one to this position, I've reconstructed this photon. Alright, so it's that simple a mechanism. So all you're seeing with the red here is you're just saying the photons that would be put back together here, this distance is the red distance. The blue distance will be a different distance, so it has to come from some sharper angle because there's less of a change, and there was no source at the sharper angle, so there's no blue photon. So from this position, this was the position of how thick these lines are. I mean, how thick these little humps are. You can only go from this. There's only certain angles that it's possible to reconstruct photons at, and that's why you see them in certain places. So the red photon doesn't get bent by the prism in a specific way that's different than the blue ones. It just has to do with the stuff that comes out and the possible angles that'll create a pattern. And so that's really all you're seeing. The light went to all these places. The little bits are hitting all of these places evenly. There's just as many little bits hitting here as there are here as there are here. And all you're going to see is where you reconstructed photons, where the angles added up correctly to create a new photon, in terms of compensating for the pieces disturbed by going through the surface. And the disturbed going through the surface, okay, so this is probably a really important feature, is to understand that no matter what, even if there's no slit, right? There's no slit on a prism. There's no obvious problem, but there is a surface, and the surface has a reflective index. So it's going to reflect a certain percentage of the light. What that means is that the photon's going to be coming in, and it's going to get broken in the sense that this little bit, by percentages, okay, say if it's 10% reflective, that means 10% of this photon, each individual photon, not 10% of the photons, 10% of the actual photon will actually reflect. That is, one of these bits has a 1 in 10 chance that it'll go this way. It'll bounce off the surface. So we know we're breaking that photon, in the sense we're knocking a piece out of it. And so it can still have whatever, 10 bits to it or whatever, a ray length. But one portion of that ray length can be disturbed, and that means the photon can't be seen now because it's doing this. It has the right frequency, and then all of a sudden there's a big gap, and it goes back to the right frequency. Can't be detected that way. It can't be detected as little hunks of a photon. It has to be a consistent frequency for a specific amount of energy. And for our eyes, that means 6 to 9 of these bits. The photon has to have a ray length of 6 to 9 bits for our eye to say, yes, that's a photon, where a frog would be maybe 3. Anyway, so you can see smaller hunks of light. A frog, he or she. I don't want to be chauvinistic to the poor frog population. Anyway, so as soon as it hits the surface, the light's broken. And then it has to go through the prism, and it can hit things, and you can see reflective light because you're going to see pieces coming off of it because of the number of photons you put through. So you're putting millions of them through, and then you could actually see some of the light inside the prism. And that's also the same angular rules. The light really isn't in there, the color. You're making the color by reconstructing pieces of different photons that have the capacity to be reconstructed into the correct frequency. So it's all geometry of angles. But But the important part to realize is that a certain number of the photons get broken off right at the surface via reflection. So they're broken photons. The broken photons go through, and some of them internally reflect, and do this. They can go in all kinds of places by the same percentage. So you're breaking them again. And so what comes out is a bunch of broken photons. But again, there's so many of them that you can just do the angular thing and figure out from what angles you can reconstruct a photon based on from what angles they can leave the surface of the glass. So depending on the angle of the light going in, the angle of the light going out will be the same, but it'll be spread over a larger surface because you diffracted in the process of refracting. You're also spreading. You're not just sending the straight beam, you're spreading the beam while it's inside the prism, because it's diffracting off the surface, which has also got atoms in it, and there's different spaces between the atoms and the electrons, and the electrons are going to interact with the photons, and the photons are going to move. All right, so it's probably enough of a premise. But the key thing I'm trying to get across is that the bits of the photon have no idea they're infrared or ultraviolet or white, or well, they're not white, but red, green, or blue. They have no understanding that I'm part of a photon that's at a specific frequency. The individual bits are just individual bits, and all you really do is mess up the bits and then reconstruct the bits. And that's what conventional physics completely fails to understand at all. All right. I mean, it's Professor Loon was always a bit of a clown, but he's getting much worse with age. So. Oh, I forgot about the commercials, of course. Apparently his pension isn't sufficient to pay the bills. Anyway.
Hello, 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 hello. Today is January 17, 2020.
Very exciting.
This is my first...
January 17. Did you just say that? Well, why are you putting a video up that's 2 months, a month old?
Recording of a new problem in the new year.
Uh-huh. So, see, no point in doing the date thing when you're not even going to publish the video on that date. Then it makes even less sense. So I just forget about doing the date thing.
We were on vacation in California and in Nevada. Great vacation. When we got back, we both got sick. I was 3, maybe 4 days in bed. Headache, running nose, fever, feeling very weak.
Yeah, well, life's tough. It sort of sucks, doesn't it? Yeah, it sucks. Yeah, I guess you got whatever, crater fever. Probably got bit by something. Yeah.
Flu-like symptoms, so to speak.
Okay, so what? Oh, sorry. I mean, I didn't watch the video ahead of time. My mistake. We'll speed it up a little.
But I've now recovered to the point that I feel comfortable doing another physics problem, which I have thought about while I was sick.
Oh, great. It's good to think about stuff, but apparently you just don't think about, well, what if we're wrong about all this waving crap and all this stuff? And, it's just too bad you never did any of that. What if? You just never did enough of that what if stuff. What if? Yeah.
It will be a problem about optics. If you have the interest to watch my lecture 18 of 803, then this problem will be a piece of cake. But that's not an easy lecture.
Yeah, that's right. So, whatever. See, so again, it's this whole thing. The problem is the math. The problem isn't understanding exactly what the causes are and the effects are. Why are there effects? What's causing them? What's the mechanical structure? Why does it happen? Those are the important things to know. Knowing that, well, I know there's a certain amount of momentum, and I know there's a bit of, all that crap isn't going to really help you any.
Your high school physics may be enough to do this problem, and that will be fine with me. But there's a little bit more to it than your high school problem. Let's first discuss the problem. This is a glass prism.
Yeah.
This surface here, and this surface are perpendicular to the plane of the paper. The angle here is 90 degrees, 45 degrees here, and 45 degrees. I have a narrow beam of green light, which has a wavelength of about 500 nanometers. And the index of refraction of this glass for this wavelength is 1.5. This beam is here.
So that's one of the interesting things to understand is the index of refraction is the same for all the lights. And then all you're changing is how much every single little bit is bent. You're not changing like blue ones bend more and red ones bend less. None of that ever happens. It's each bit gets bent a certain amount, and all you're talking about is the display. Where you're going to be able to reconstruct photons changes based on how much you bend the little bits. So if you bend the little bits more, you'll be able to reconstruct the photons at a different angle than if you bent them less. And that's all that's going to change. So again, there's no blue photon has a different index of refraction. It all has the same index of refraction. All it's going to do is when you change the index, you will change the position at which you're going to see that color after it goes through the prism.
Perpendicular to this surface. We call that normal incidence. The plane of incidence is always defined as the direction of the light and the normal of that light.
Yeah, so he's not really using the prism the way you usually use a prism, which is coming in at a 45-degree angle. And so, trick question or something.
And so the normal to the surface, the normal to the surface. And so the normal to the surface is in this direction, and this is the direction of the light. So this is the plane of incidence.
So let's concede again. There's going to be a certain amount of reflection off the glass, and with a prism, I think you're doomed to some portion of the glass will reflect more than other portions of the glass. So some portion of the photons get broken right from the start. As soon as they hit the surface, you're already starting to take pieces off of the light. You're destroying the photons a little tiny bit at a time, maybe 6%, maybe 10%.
The light intensity on this surface is capital I. So something is going to happen here, and then when the light reaches this point here, something is going to happen here, and when the light comes out in this direction, something is going to happen there. And you will have to deal with that something. The question is, what will be the light intensity?
Well, they're all transmissions, and there's no phase shift on light that transmits, that goes through. So it's only on reflections off a higher medium, a higher index of refraction that you get these things called phase shifts. So that was something I did want to say in this video, but I just never got around to it. Was the curious, like once you understand that light does have a polarization, and the fact is that it's moving through space with things out of perfect alignment. So if you imagine this is the photons, a group of them, all right, they have an alignment with each other this way, but that's sort of cheating the single photon. The single photon is going to be it's going to have a polarization, but the polarization is going to be spatially something like that or whatever. So the idea would, let's make it even higher. Well, the idea is the light doesn't come in. It comes in with this polarization, so it has a thickness to it where these little bits are coming in. So you could think of it, just for the sake of the argument, let's just say it's a line like this with little bits. And so when it comes to a surface at an angle, what's going to happen is yes, of course, this bit is going to hit first, and it's going to reflect, right? And then this bit's going to hit last, and then it's going to reflect here. So what you've done is reverse their order. The one that was on top before is now on the bottom of the new ray, and the one that was at the bottom of the old ray is now going to be at the top. And that's something they don't talk about. Okay. And it's that's causing what you could argue is the phase shift, is the loss of momentum involved in the flipping of the object, a rotation. So that's the loss of time, is in rotating. So you didn't just bounce off, you rotated. So you went from this to this to this to this. You rotated through space, and that rotation is the phase shift. That's what took time. So anyway, just a way to understand why, when you're reflecting off the thicker material, you phase shift. It's because you're going to, that's what's going to happen. And you don't, have to think about that for a minute. You don't reflect off lighter surfaces. Yeah, you only transmit out into lighter surfaces. That's why you don't get a phase shift going to a lighter medium. It's because the lighter medium doesn't force you to reflect. You're reflecting off the interior thick surface. You're not reflecting off say if I'm going out into the atmosphere, I'm going to have the change is going to happen on the outside of the surface of the thick thing, not on the inside surface of the thin thing. I'm going to reflect off the thick surface, not the thin surface.
That comes out in this direction. And as I said, it's perfectly okay if you have sufficient high school knowledge to do this problem. If you learn more physics than is covered in high school, you will learn that what happens here and there depends on the degree of polarization. And a distinction is made in the so-called Fresnel equations between light that is linearly polarized in the plane of incidence and the light that is linearly polarized perpendicular to the plane of incidence. If it were polarized in this direction, it would be perpendicular to the plane of incidence. If it were polarized in this direction, it would be polarized in the plane.
Right, so the basic argument is this one I just made. The one surface, the hypotenuse of that triangle, the bottom of how we want to describe it, is the one you're going to reflect off of. And the reflection, the phase shift, if the light's coming in this way, like these little dots are all going in and out of the board, well then they all hit at the same time and they all bounce off. But if it's coming in this way, then it's going to be this thing where they're not going to hit the same time. They're all going to hit at different times. And so that's what he's saying, is the outcomes will be different if you use light that's already been converted through a filter to be only in one polarization. Now, my argument would be is that even when you think you've converted light into one polarization, you really haven't, because the other light is still there. It's just not in a form that's easily reconstructed. It's broken, and you're going to put it through another thing that breaks it, and you're not going to be able to remake it because you broke it too much. But it's still there.
And the Fresnel equations make a difference between the two. They discuss for each individual polarization what happens. So for those who are advanced, I would like to know the same answer. What is the intensity of the light that comes out here, if this is capital I, if the light were linearly polarized in the plane of incidence, and what would be the answer if the light were polarized perpendicular to the plane of incidence? But for those who have never dealt with the degrees of polarization and the direction. Use your high school knowledge if it is enough, and chances are that your answers are correct. Okay. Lecture 18.
So intensity is just you're saying how much of the light is reconstructed. And again, I don't know if they ever even bother to test that empirically. That is, to actually do an experiment to see what the actual intensity is.
803. It's all there, but it may blow your mind. It's not my intention. All right then. I don't know when I will publish this, when I will post this. It is January 17, 2020.
You know, he could put a link into his own
outside
video.
Temperature is about -8 degrees centigrade. Very, very cold. That's not why I'm wearing this. I always wear this inside. I like that. All right then. So in the
Yeah, well, no accounting for taste, as they say, and such, so forth and whatnot. So it's probably enough. I will just play the end.
year, have a nice day. Take care. And surely, in 2020, we will again be friends.
No, well, whatever. You're not really that friendly. You know, it's just a pretense. You know, as long as I behave appropriately. You know, it's very conditional love you get from people. Love, 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 love. As long as you do and say exactly what I want you to. All right. I'm just saying, that's the way I am. So there's nothing wrong with that, but just don't be dishonest about it. All right. Anyway, so is this probably enough? It's probably enough. I'll say it's probably enough. Because yeah, the other interferometer stuff. Well, I could do a little interferometer stuff. What the hell? Maybe I'll put the. I took the video off, so I can't put that back on. So we'll just see what we got over here, maybe. This might be it. Video I took the clip from. Yeah, okay. There it is. Alright, so they don't really account for a lot of things in interferometers. So yeah, something that did seem very curious to me was recognizing that the one path is actually the filtered path, which is sort of interesting. And what we do know is like the beam splitter too, in theory, okay, you're going through the beam splitter with one path and you're going reflecting off it with the other path. And the reflection isn't diverging, but the path that goes through is going through a bunch of little gaps, and those little gaps are going to cause the light to spread. Okay. And what they don't talk about is the fact that if this goes any kind of distance, this spreading, there's no chance that when it goes back, the light, it's certainly not going to go back through the same holes in the mirror that it went through, right? There's no chance that it goes back through the holes because it reflects off the mirror. So they're already conceding in a sense that none of these beams or rays are going to be perfectly represented through the process and then come back exactly the same path, because if they did, they go straight through the mirror and you'd never see them again. So they obviously have to come back some different path to actually hit the silver. They went through the gaps. And when they come back, they're going to hit the silver. Well, the only way they can hit the silver is their path has to have been changed by the process of going through the interferometer. So anyway, so the point is this beam is spreading the whole time. And what that sort of means is when it comes back, it's going to be lost, in the sense you've lost a bunch of the photons because they've spread to places where they can't get back. There's no mechanism to bring them back. So when it's coming back to the mirror, so let me get rid of the going into the mirror part, and we'll just have it coming back from the mirror. So it's coming back from the mirror, spreading this way. And the problem with that is that's going to create angles like this and angles like this. And so it's going to spread it even more. So there's no chance that the other beam is going to come back and it's going to just spread a little bit here. So you're going to be looking here with your eye. Okay, put a little eyeball in here. You're going to be looking at this little piece. So obviously a lot of this light is gone. Okay, it's not even part of the experiment anymore. Can't possibly influence anything. And so the trick is that what you're really looking at is that some of the light that did go through didn't get diffracted. So whenever there is an opening, a single slit, some of the light does go right through the center, doesn't get bent. And so that light is really the light that went through all the mirrors. It's coming back, and that's what you're seeing here. So you're really going to be mixing very parallel beams, okay, with the diverging beams coming out from this direction. So this thing's creating a straight line coming here, and then it doesn't diverge to the last little bit here. All right, so those are the two beams you're mixing. You're mixing parallel light and diverging light. So that's an interesting fact, never dealt with in any of their descriptions of the reality. And the percentages are clearly, you've lost maybe, I don't know, let's say you've lost at least 20%. Well, it's probably more than 25. 25% of this beam you've lost. So now you really have a proportion of, you're using, 70% of the beam that's now the diverging beam, mixing it with 30% of parts that are straight line at best. It's probably even a bigger differential than that, but who knows. So that's just all part of the interesting facts. And what's really going to happen is you're really mixing the phase of the stuff coming straight with the phase of the stuff with the longer lines. So again, that's what's creating the rings, is you've got a straight piece and then a bent piece, and it's going to be at certain frequencies would be a wavelength difference. So this will be one wavelength, and then this will be two wavelengths. And again, you're always mixing with a parallel. And so those will flip the other way. So obviously you also have the circumstance from this side, and then you also have the circumstance where it's, from this side. And that's what's creating your ringed pattern, is where you have a full wavelength of path difference. It'll create a light where there's a full wavelength. And the black line is really just representing where it's too much in between. So you can get away with being a little bit off. 270 might be the same as 300 nanometers. So these don't have to be exactly 300 each time. They can be close. This one's 270, this one's 300, that kind of thing. But if they're enough off, and this is 260, well then this part of the photon, this photon can't be reconstructed as a red photon. So that's where you have the black line, is where the phase is enough off where you're getting close to being some other frequency. And when you're some other frequency, you can't be detected as any frequency when you're a mixture of frequencies. So a photon that has a mixture of frequencies can't be detected as either frequency. So if I have like well, that's a good enough way to illustrate it. I have 1 inch of difference, then I have 1 1/4 inches, and I have 1 inch and 1 inch. I can't put this wrong frequency in there. And that's what the black lines represent, is where you can't reconstruct a photon. So the light went to all these places is semi-evenly. And all you're really doing is saying, where can I put the photon back together? And where is it impossible, because the path lengths aren't right. They're half of a frequency rather than a whole frequency off. And so that's all there is. There's either reconstruction or no reconstruction of the photon. So I know there was some other bit. And of course, I'll ask this question to the people who defend LIGO and all this other stuff to give me some explanation for how they can account for the simple fact that mirrors aren't perfect. So when light hits a mirror, it goes in and it can hit the 12 atoms deep, or it can hit 6 atoms deep, or 3 atoms deep. So it's constantly, each photon, each little bit of the photon goes to a different location in here. And so each time you go into the mirror, you could be losing 6 nanometers worth of of distance. And they say that LIGO reflects back and forth 1,600 times. So 1,600 times you're doing 6 nanometers, or let's just say it was 5. nanometers worth of damage, well, that comes out to 800 nanometers of change you could be creating inside the, in terms of the length that the beam is measuring. So how can you measure half the distance of a proton when you can't be sure how irregular this distance is? Each time you do the experiment, you're going to get a different precise measurement of the actual distance, because the mirror doesn't have a specific location. The mirror is, 10 atoms of movement already exists in the surface of the mirror. Now, I haven't heard them say that they've made mirrors that are perfectly reflective, that reflect right off the first atom each time, so it's the same exact location, the same distance, right? This is a distance argument. They're saying they can measure half the distance of a proton in the movement of this mirror, when we can't guarantee that the photon itself didn't reflect from some other portion of the mirror. So how could they possibly measure that? How could they have that much precision in an instrument that you can't make the mirror that precise? You can't make a mirror where you can say the surface is within half a proton of a certain distance, because the atoms on the surface of the mirror aren't that perfect. So anyway, all right, enough said. Yeah. So till the next time and such. I believe that's enough for now. And that'll do.